Okay, we're going to do addition across a double bond. So, our example today is propene. We're going to do addition of hydrochloric acid across the double bond in propene. So, the first thing we need to do is think which is our nucleophile and which is our electrophile. Well, as you know, hydrochloric acid is a strong acid and it has a tendency to split up into H plus and Cl minus in any kind of solution, or H3O plus and Cl minus or chloride in water. But it will split up quite happily in any solution that has lone pairs because it is quite a very strong acid. So that hydrogen that has no electrons is going to be our electrophile to start things off. This double bond, if you think about it, has two pairs of electrons in the space of the carbon-carbon double bond. So it's actually quite electron rich. And so that second pair of electrons, the ones that are in the pi bond, are capable of acting as a nucleophile. So if I draw in this as H plus, and I can put it in inverted commas because we know that H plus doesn't really exist, it's always attached to some lone pair, and I draw back out my chloride over here. It's going to be happy, it'll be solvated as well, and I draw in my double bond. Well, now it's easy to see my electrophile and my nucleophile. So let's draw an arrow going from the pair of electrons that's going to form a new carbon-carbon bond. Well, we have a choice here. So we know this is a pair of electrons that's going to form the new carbon-hydrogen bond. Might have said carbon-carbon a minute ago, but it's going to be carbon-hydrogen because this is a hydrogen. But is it going to form between this carbon and this hydrogen, or this carbon and that hydrogen? Well, let's investigate both of them. So let's investigate with the purple and go that way. And if we do that, what do we get? Next step, well, the same rules that we always follow. Draw out everything that doesn't have an arrow going from it because it'll still be there. We haven't moved those electrons, so they have to still be there. Chloride will still be there. And what did we do? Well, we said we're going to put it here. So we took this pair of electrons, put them here. The hydrogen is now sharing a pair of electrons, so it's neutral, and our positive charge has ended up on this carbon here. The alternative is that we take this pair of electrons and we form a new carbon-hydrogen bond on that side. Where does that lead us? Well, I'm going to put this one in orange just so we can see the difference. So in this case our hydrogen is here and our three carbons are there, and we took this pair of electrons and we put them in here, and the positive charge is now here, and we still have our chloride. And so the question is, which one of these is more likely? And the rule that you want to apply is Markovinkov's rule, and it says that the atom with more hydrogens in the first place is the one that gets the hydrogen in the reaction. So in this case, this carbon would have two hydrogens, and this one would have one hydrogen. So it would make sense that if we follow Markovinkov's rule, the orange pathway is the pathway that we go. This one has less. This is not the pathway that we go. But we can explain a little bit further. If you've read about carbocations or you've met them yet, you'll know that the more substituted a carbocation is, so a carbon with a positive charge on it, the more stable it is. So here we're making a secondary. There's two carbons bonded to this carbon. We're making a secondary carbocation, and here we're making a primary carbocation. And so the energy, or this, is going to be less stable, and it's going to be a higher energy state than this is. So to go from here to here requires a bigger jump in energy than to go from here to here. And so this is where the reaction pathway is going to end up. Well, what happens next? We've still got electrophiles and nucleophiles to think about. This is a fantastic electrophile. It's a carbon with a positive charge, and this is an alright nucleophile. So this pair of electrons is going to form a new carbon-chlorine bond, and we can draw out the product of our reaction, which is going to be the addition of hydrogen chloride across the double bond. There are exceptions to Markovinkov's rule. So there are exceptions where you can use different reaction mechanisms and use radicals, but there are also exceptions in that you can set up conditions where just because it's a more substituted carbon doesn't mean it's going to be more stable. So an example of that would be, for example, this molecule here. By putting lots of fluorines onto this carbon, it becomes much more electronegative, and so having a carbocation here is going to be less stable than having a carbocation here. So what's the product of that reaction going to be? Well, that reaction, we add in hydrogen chloride. In this case, we're going to end up with a chlorine here and our CF3 group over there. There are more examples than that as well, but that'll do for now to give you some idea that Markovnikov's rule applies in nearly all cases, but sometimes it doesn't, and if it doesn't, you have to follow the logic of how Markovnikov's rule came into existence. Okay, I hope that helps. If you have any questions, post them below or up on Moodle or ask me in class. That's all for now. Bye.